Hello and welcome. Today we're going to be looking at the unit test for infinite sequences and series. This is the last unit on AP Calculus BC. This one isn't even in AP Calculus AB. As always, we're going to be going through all of these questions to make sure you understand how to approach and solve these questions. I know that this topic is extremely difficult and there's a lot of content to get through, so we are going to make sure that we learn every single question so that we're ready to ace the AP exam. If you like these videos or find them informative, please be sure to like and subscribe. And with that, let's get started on our first question. Here we go. All right, we're taking the int sum from n equals 1 to infinity of 3 times x plus 1 to the n over n times 4 to the n. What is the interval of convergence of the series? Okay, so what do we know? What do we know here? Well, we can write this as 3 over n times x plus 1 over 4 to the n, like this. And this is how I've written it. We can write it like that. Okay, now let's see. So we have x plus 1 could be going to 4, or it could be going to negative 4. Now, if x plus 1 is less than 4 and bigger than negative 4, then you're going to get x plus 1 over 4 is going to be less than, or it's going to be absolute value less than 1, meaning that it's going to go to 0 and it's going to converge, most likely. All right. Now, so let's see what we can do. So we know that everything in the middle between negative 4 and 4 will converge. All right, because if you plug in 4 for x plus 1, then you get 4 over 4, negative 4 over 4. All right, now if you make x equal to 3, so x plus 1 is 4, then you get 4 over 4, so 1 to the n, which leaves 3 over n. Now 3 over n by itself is the harmonic series, which doesn't converge. So just x plus 1 is 4, or x is 3 doesn't work. Now, if we go the other way, x plus 1 equals negative 4, which means x is negative 5, that would give you negative 4 over 4 to the n, or negative 1 to the n, which is the alternating harmonic series, which does converge. All right, so essentially we have negative 5 works. It's going to be negative 5 less than or equal to x. 3 doesn't work, so it's just going to be less than 3. So it's going to be like this. Negative 5 is less than or equal to x is less than 3, and our answer will then be C. And we can keep going to the next question. Now we have 2 over 1 plus 2x. Well, we know that if you have something over 1 plus something, right, this is going to be the formula for the geometric series, right? So our formula is the 1 over 1 minus something. Here, we're doing 1 minus negative 2x. Gives you the 1 plus 2x. So it's going to be, say, 1 plus negative 2x to the first, plus negative 2x to the second, plus negative 2x to the third, and so on and so forth. But this whole thing is also going to be multiplied by 2, since we have that 2 in the numerator. So we end up with 2 minus 4x plus 8x squared minus 16x cubed, and on, which is going to be D right here, and we can keep going. All right. Now we're given f of x equals the sum negative 1 to the n, x to the 2n plus 1 over 2n factorial. Find the power series for f double prime. Okay, f double prime. I'm trying to find the power series for that. Let's see. How do we find the power series? Well, we can write each term as negative 1 to the n times the x 2n plus 1 over 2n factorial, given any n. Now, if we take the derivative of this, what do we get? So negative 1 to the n. So what does that really do? Well, that's going to, if we take the derivative of that, that's an exponential. So we're gonna have to try to take like so it's gonna be the product rule, right? Negative 1 to the n times the x to the 2n plus 1 over 2n factorial, right? So we take the derivative of this first one, that's going to give you ln of the absolute value of negative 1, which is ln of 1, which is 0. So that's going to cancel out. So the only part you are going to get is going to be the x to the 2n plus 1. So you have 2n plus 1 times x to the 2n over 2n factorial times negative 1 to the n. Now remember, x is the only thing that like actually is a variable. Everything else is just n is a number. Right? N is a number. Now you take the derivative of this again, you get 2n plus 1 times 2n over 2n factorial. So the 2n's going to cancel out, and you're just going to left with 2n minus 1 factorial. Still times negative 1 to the n. So you're going to have negative 1 to the n times 2n plus 1 times x to the 2n minus 1 over 2n minus 1 factorial, which is going to be that one right there. And we can keep going to the next question. S equals the sum from 1 to infinity of n squared plus n over n cubed minus 2n plus 2. What series should we use a limit comparison to determine whether S converges? Well, let's see. Well, it's the same. The way we do this here is the same way that we determined back in like pre-calculus when we had our these kind of polynomials dividing each other. If it was going to go the n behavior, right? If it was going to go to infinity or to 0, we take the highest degree term. So that's going to be n squared and n cubed, which we can simplify to 1 over n. So our comparison has to be to 1 over n, which is a right here. Now 1 over n diverges, which means that this is also going to diverge. And we can keep going. Alright, the nth partial sum of the series S is given by n squared minus 1 over n plus 1. Now I can write n squared minus 1 as n minus 1 times n plus 1. So it's going to cancel out the n plus 1 on the bottom and just leave you n minus 1. Now if we're trying to determine S, that means that n becomes infinity. So we have n minus 1. If n is infinity, then S diverges. Let's keep going. Following infinite geometric series converges, find its sum. Oh. But wait a second. Let's look at that for a second, okay? So we're doing 1 minus 3 plus 3 squared minus 3 cubed. It's going to be plus 3 to the 4th, minus 3 to the 5th, plus 3 to the 6th. It's going to become really, really, really big. Like, massive. We're going to end up with like 3 to the infinity or something. Right? It's not going to converge to anything. It's just going to keep getting bigger and bigger and bigger and bigger, on and on and on and on and on. Right? It's never going to converge. It does not converge. Right? It only converges if the terms go to 0. Right? These terms are not going to 0. They're going to infinity or negative infinity. So it doesn't converge. That's the nth term test, remember. Let's keep going. All right, limit as n approaches infinity of n factorial over 1000 to the n. Okay, so as n approaches infinity, well, n factorial is going to grow bigger than 1000 to the n is, because like if you do 1 more than n, then the numerator gets multiplied by 1000, but the denominator gets multiplied by 1000, but the numerator gets multiplied by like infinity. Like it could be like a million or a billion for all you care. All right, so it's going to be massive. That's going to be going to infinity. All right, so it's going to infinity, so the terms are never going to converge. Terms are never going to converge, meaning that the series diverges because it fails the nth term test. And we can keep going. All right, estimating sine of 0.4 using Mclaren Polynomial. What is the least degree of the polynomial that assures an error smaller than 0.001? Okay, so we're going to have to bust out the Lagrange error bound for this. Lagrange error bound. I know it's not an error bound that most people like. Right? The alternating series error bound is much neater and stuff, but this is a necessary error bound to learn. Right, so the Lagrange error bound is going to be it's going to be f, going to be the nth derivative of something of this function sine of sine of x, where x is 0.4. And then it's going to be Lagrange error bound. Right, the next part of the Lagrange error bound is going to be it's going to be hold on. So the Lagrange error bound, right? How do we use the Lagrange error bound? So the guiding principle of the Lagrange error bound is that you have the greatest that you have the greatest like derivative in that range, in the range that you're operating in, and then you raise that to some powers, or you raise the derivative to some powers, and that's how you get the amount of error that you could have. And that's how you can get the amount of error that you would have. So now, if you wanted to see how this would work, if you wanted to try to write out the Lagrange error bound, right? Then how would you do that? So the Lagrange error bound has notation f of n sine of x over n factorial. Right? If you recall, the n factorial is so that when you keep taking the derivative of something, it cancels out with that stuff, right? So n factorial times x minus 0.4 in this scenario, right? Whatever's inside that's functioning as x minus 0.4 to the n. Okay, so now what we do, right? Since we're using a Mclaren polynomial here, actually, right? So if we're using a Mclaren polynomial, right, that means that it's centered. Oh, threw my pen. That means that it's centered at 0. Okay, so it's centered at 0, so it's going to be f of n sine of that x in here is going to become 0. That x minus thing, that c, that's also going to become 0, right? So it's just going to be x to the n, really. Right, and that becomes what? Well, another one where this whole thing, where really what we have is just 0.4 to the n over n factorial. And we're just trying to find the least degree of the polynomial that satisfies that. Now we can just like plug some numbers in. 0.4 to the 5th over 5 factorial. Let's try that. That gives us this as our error bound, which is like really tiny. So that would definitely work. Let's try 4. That would give us 0.00106. It's like this close, except that it doesn't work. So our answer is going to be 5, and we can move on. Okay, we can't move on to the next question. We have to think about why this is incorrect. All right, so if you look at this again at 4, you'll realize that there's one small thing that actually changes everything, and it's the fact that you have an n plus 1 here instead of just n. All right, the same way with the alternating series error bound, where you look at the next term, or you look at the first term that you skipped. If you're trying to find the error bound, you look at the next term, right? The first term that you skipped, first term that you didn't include. That's the same thing here. You have to do n plus 1. All right, so if we're hitting 5 or something that is small enough, that means that 5 minus 1, well, the 4 is going to be what you put in for n plus 1. So our answer is going to be 4, actually. And we can keep going to the next question. All right, f of x is going to equal negative 4x cubed plus 3x squared minus 6x plus 10. What is the coefficient for the term containing x minus 3 squared and the Taylor polynomial centered at x equals 3 of f? All right, so this is centered at x equals 3. And we're trying to essentially find the Taylor polynomial for this. So how are we going to do that? The same way we find any Taylor polynomial. And so let me turn to a new page. And we'll start thinking about how do we construct a Taylor polynomial, right? How do we construct a Taylor polynomial? Well, remember that we construct a Taylor polynomial by finding the derivatives. So we find the 0th derivative, we just plug 3 in there. We find the first derivative, find the second derivative, and then we divide by the 2 factorial, then by 3 factorial, and 4 factorial, on and on. But we actually only need to go 2 places, so we only need to divide once. So if we're doing that, right, then we just need, first what we're going to do is we're going to plug in 3 into this equation, f of x. And we get, what do we get? Negative 4 times 27, that's actually 3. 4 times 27 plus 3 times x squared, which is 9, minus 6 times 3, plus 10 is going to equal negative 108 plus 27, negative 81, minus 18, negative 99, plus 10, negative 89. Negative 89. Alright, and now that's going to be the first thing now, unit f prime of x, which is going to equal negative 12x squared plus 6x minus 6. And the 10 cancels. And we could calculate this, and you really don't need to calculate it to find the second degree term, but we're just going to do it just for practice sake. When you plug in 3 in here, you get, what do you get? You get negative 12, that's negative 108, plus 18, which is going to be negative 90, and then minus 6, negative 96. And then f double prime of x is going to equal negative 24x plus 6, negative, it's going to be what? Negative 72 plus 6, negative 66. But of course, this is 2 factorial. This is the second derivative, so you have to divide by 2 factorial, which is 2, which is going to give you negative 33 as that coefficient. So our answer is negative 33. And we can keep going to the next question. Evaluate the Mclaren series. Oh god. Oh god. Okay. How are we going to do this question? Let's see. How are we going to do this question? So obviously, we're going to have to try to change this into a version that's like an actual function, right? So what I see when I look at this is that is essentially you have pi over 2. It's what I'm looking at this. I'm just going to rewrite this as pi over 2 minus pi over 2 to the third, right, over 3 factorial, plus pi over 2 to the fifth over 5 factorial, and then so on, so forth. Okay, so if we're doing it like that, what does that mean? So which one of these has, when you take the derivative, the first derivative, it gets you that. Well, if you take the derivative of sine, do sine of x, it would give you that, wouldn't it? Yeah. If you took sine of x, and then, so the first derivative is going to be cosine of x, and that would give you the 1. The third derivative would give you negative 1, right? And then the fifth derivative would give you positive 1, and then on, so on and so forth. Okay, so what is that? What is that? Why do we care? Why do we care? What does that mean? Right, it means that instead of putting pi over 2, we can put an x in there. All right, so essentially we're just saying sine of pi over 2. Why are we saying that? Because the sine of x, the Mclaren series for sine of x, is x minus x cubed over 3 factorial plus x fifth over 3 factorial, so on and so forth. Instead of x, we're putting pi over 2. So instead of saying sine of x, we're going to say sine of pi over 2, which is 1. So our answer is just 1. That's all there is to it. Let's keep going. The nth partial sum of the series, that sum is given by Sn equals 3 minus 8 over n. Asking us for A8. Okay. So how are we going to figure that out? Well, the thing about partial sums is that, let's say S7, the seventh partial sum, is going to be A1 plus A2 plus A3 plus A4 all the way up to A7. And S8, the eighth partial sum, is going to be the same thing plus A8, which means that A8 is just going to be S8 minus S7. So we just plug in 8 and 7 into this partial sum formula right here, and you calculate what it's going to be. All right, so S8 is going to be 3 minus 1, so 2. S7 is going to be 3 minus 8 sevenths, so 2 minus 1 seventh, so 13 sevenths, and it's going to give you 1 7th left over. So A8 is going to be 1 7th. 1 7th. And you can always do this when you're dealing with these partial sums, right? The difference between two partial sums is going to be that term that you just added in. So you can find those terms by subtracting, by finding the difference between those partial sums. All right, here we know that 1 over 1 minus x equals 1 plus x squared plus x cubed, on and on, because that x right in here is going to be, that x right there is going to be what is the geometric, right? Because you have 1 minus something, and that something is the x is going to be the geometric series. Using the fact, we're trying to find a function that corresponds to the following series. Okay. What do we have here? Well, I think something to notice is that it's not like x squared over 2 factorial plus x cubed over 3 factorial. It's just over 2 over 3 over 4, right? So it's different from what you would usually do. Let's see. Well, I think something that's really interesting here is that something that you got to really look at a bit carefully to see. If you take the antiderivative of this, you get that. Take the antiderivative of that, you get that, and that to that, and then like this goes to that. All right, which means that this is just the antiderivative of that. If you take the derivative of this, you get that, and this is equal to 1 over 1 minus x. So we're just trying to find the indefinite integral, the antiderivative of 1 minus 1 over x, which of course is going to be negative natural logarithm of 1 minus x. Negative natural logarithm of 1 minus x. Right, so if let's see, which one's that? That one is this one. Oops, that one is this one right here. Right, if you have this and you take the derivative of that, then you end up with 1 over 1 minus x. Right, because the negative sign is going to cancel out by the chain rule, that negative there. And it fits, right? If you think about it, right, if for all x in between negative 1 and 1. All right, so if you put in like negative 1 into here, that's going to give you something negative ln 2, so it's going to give you negative. Well, if you put it in here, this is actually going to give you something positive, 1 over 2. Right, that seems a bit suspicious. Right, if you try 1 in here, then that's going to give you 1 over 1, well, obviously, 1 won't work. If you try in like something 0.5, that's also going to give you something positive. Try 0.5 in here, it's going to still be negative. Right? Or it's actually it's going to be the ln of 1 minus 0.5, which is going to be 0.5. So ln of 0.5 is going to be negative. It's going to make that positive. So it's kind of interesting to think about, what is that going to be? Is it going to be positive or negative? Like how does that work? And this is the reason why we put like absolute value signs in that, because it's really important to think about it that way, or else everything just gets completely screwed up. Right? But if we're really going to think about it, we have to think about the fact that if we plug in what, right? So if we take the derivative of this, we get that. If we take the derivative of that, you get negative that. All right, so that is correct and that's not. Right? It might be difficult to think about it that way, but that is just how it works. So let's keep going to the next question. Okay, so you have a of n equals n squared plus 6n minus 2 over 2n squared plus 3n minus 1. We're trying to find the limit as n goes to infinity of a of n. All right, so I think we've been in this kind of territory before, right? This is our pre-calculus work, all right? This is what we learned in pre-calc coming back. We're going to infinity, so we're just going to take the highest degree terms. N squared over 2n squared is going to equal 1/2. Same degree, so something actually happens. We actually can have some fun. It's going to be 1 over 2, not 0 to infinity, 1/2. Let's keep going. All right, so you have the sum of minus 1 to the n plus 1 over n. It's approximated using the partial sum goes to 99, which is a pretty decent partial sum, honestly. The error bound. Okay. The error bound. What's the error bound? This is a alternating series. So the error bound is just going to be the next neglected term. We stopped at 99, so I'm going to put in 100 as n. If I put in n as 100, then I get negative 1 to the 101, which is going to be negative 1 over 100. So that's going to be negative 0.01. Oops, probably turned that up. Negative, it's going to be negative. It's going to be negative 0.01. So the approximation is an overestimate. So negative 0.01. Right, so it's an overestimate. Okay, so what is it? Why is it an overestimate? Because I just added something, right? Now, if I did the next term, I was going to subtract something to get closer, right? So it's too much, and I'm supposed to subtract something the next term. But I didn't do that next term, so it's an overestimate. Let's keep going. Oh, and it told us that this is actually incorrect. Why is this incorrect? Let's see. Right? Let's think about why this. See, this is the error bound right here. The error bound is negative, and the approximation overestimate. And the absolute value, this thing here, is just us not being careful. 0.01, this asks for the absolute value of the error bound. make sure you are careful. Make sure you read the question. All right, even if you've done it lots of times and you feel like you have that practice, it might still like just be something that simple as saying absolute value, and that you have to check out to make sure that you're answering the right question. All right. A of n equals -1 to the n plus 1 times n plus 1 to the fourth over 4n. Find the limit as n approaches infinity of a n plus 1 over a n, absolute value. All right, so you're going to get a -1 in there, but that's going to cancel out because absolute value. You're going to get like n plus 1, n plus 2 to the fourth, which is that's not really going to make that much of a difference. But then you're going to get 4 to the n plus 1. Okay, so you're going to get an extra 4 in there. Okay, that 4 is going to go to the bottom, and that's going to give you a 1 over 4, which means it converges. All right, let's keep going. Does the integral test apply to the series? What are the conditions of the integral test? First condition, it's positive. Is it positive? You're starting at ln of 2 over 2 squared. ln of 2 is, remember ln is based on e base e. E is 2.718. ln of 2 is not going to be positive. It's going to be negative. You can't use it. It's not positive. It doesn't apply. Let's keep going to the next. Actually, wait. So it does actually apply. Let's see why it does. Right. So it's positive for everything that's greater than or equal to 2. Right. So if you can try ln of 2, right, you realize that it is positive. And why is that? There's actually this thing in there. It's very close to each other, right? That's very two close ideas that you have to make sure you realize. This idea is that if you have something ln of something that's less than the base, that doesn't necessarily mean it's negative. If you have something ln that's less than 1, then it is negative, or 0 if you have ln 1. All right, if you have log base anything of 1. All right, this is going to be less than 1, but it's not going to be negative, so it will apply. Right, of course, the other conditions of the integral test are that it's continuous, has to be continuous, and has to be decreasing. Remember, if it's not decreasing, then then it's going to fail the nth term test anyway, so it's going to diverge anyway. All right, so let's keep going. All right, so we know that z is less than, why did I say z? 0 is less than n squared minus 2 over n to the 6th plus 1, which is less than n squared over minus 2 over n to the 6th, which is less than n squared over n to the 6th, which is equal to 1 over n to the 4th. So we know that this thing we have right here is going to be less than 1 over n to the 4th. And 1 over n to the 4th converges. So it's less than something that converges, so it converges. Let's keep going. Right, so now we have S1 equals the equals the sum of -1 to the n times n squared plus 1 over n squared. Right, S2 is the same thing but without the -1 to the n. Which series converges? Well, for both of them really, if we plug in infinity as n, right, then we're just going to get infinity over infinity 1, right, because it's going to be the same thing. So you're never really going to get to 0. None of the terms are ever going to go to 0, are they? They're going to get smaller and smaller and smaller, but they never get to 0. They just go to 1. So that means they failed the nth term test. So they're never going to go to 0. They're never going to converge. So our answer is neither. Neither. Based on our answer, what can we say about S1? Well, what can we say about S1? Let's see. Well, let's see. Well, neither series converges. Well, if neither series converges, that means that the series diverges anyway, right? So that's our answer, and we can keep going. 1 plus 1 over 2 to the 7 plus 1 over 3 to 7, and on and on. Is the series convergent or divergent? This is our p series, 1 over n to the p, right, where p is a number. P is 7 in this scenario. Remember that if p is bigger than 1, it's going to converge. P is 7. This is our p series, it converges. And we can keep going to the next question. What are all of the positive values of p such that the sum -1 to the n plus 1 times p over 6 to the n converges? All the positive values, let's see. We plug in anything greater than 0, right? And then we can go anything up to 6. Does 6 work? If we plug in 6, we get 6 over 6, 1 to the n, -1 times n plus 1. Well, that just keeps going on and on and on forever, does it, right? So that's not going to work. So our answer is that. All right, so that was this unit on infinite sequences in series, the last unit of this AP Calculus BC class. One of them that's extremely difficult, has so many rules to memorize, and is just a general pain. But I hope you learned something from this video, and I hope you enjoyed it. And I'll see you next time when we continue looking at more things in math. I'll see you then.